Good day, sir. I'm Dineshwari Thanasakaran from Group B, and today I'll be presenting about uh, the pneumatic actuator control system as shown in figure Q1A over here. So for my part, I'll be showing you on how to plot the root locus for the system. So first of all, we have to come up with the transfer function, and this transfer function we can get by cascading all the elements over here. So the transfer function that we got is 5k over s to s cubed plus 3s squared plus 4s plus 2 and also s plus 2. So in this case we don't have 0 and we only have 4 poles. So the poles that we got are -1, -2, -1 plus j and also -1 minus j. So to find out the sigma A, we have to take the sum of finite poles minus with sum of finite zeros divided by the number of branch. So since we don't have finite zeros over here, we just take the sum of finite poles, and we got -5 over 4. So this is the number of branches that I mentioned just now. And to find out the angle, we have to use this formula 2k plus 1 times 180 divided by number of branches. So we got 4k, which are k equals to 0, k equals to 1, k equals to 2, and also k equals to 3. So the angles that we got are 45 degrees, 135 degrees, 225 degrees, and also 315 degrees. Next, we have to find out the JW crossing point. Since we have 4 angles over here, so there will be 4 uh, asymptote lines. Yeah, so there will be 4 asymptote lines, and we have to find out the JW crossing point. So first column here we have s to the power of 4, s to the power of 3, s to the power of 2, s to the power of 1, and also s to the power of 0. So the second column here, for the first 2 rows we just fill in with the information above, and for the third row, second column, we have to take 1, 5, and also 10, 10 over here, and we'll get the answer when we do the calculation like this. And for the third column over here, we have to take 1, 5, and also 4 plus 5k and also 0. So we'll be getting this answer. And for fourth, uh, fourth row and second column, we have to take 5, 8, and also 10 and 4 plus 5k. So for third column, fourth row, we need to take 4, 5, 8, and also 0, 0. Since 0 is involved over here, so the final answer will be 0. So for s naught, s to the power of 0, we got 4 plus 5k. And from that, from the row of 0, s1 over here, we can find out the value of k, and the value of k that we got is k equals to 2.4. So by using the k to equals to 2.4, we can substitute that into this row in s2, and we will get s equals to plus minus j 1.414, and this is the JW crossing point. Next, we can find out the breakaway point by taking the denominator and making it equal to 0. So the k that we got is over here, and later we have to change it to sigma, and we have to differentiate that in terms of sigma. And the value of k that we got is 1.6058 and also -1.072 plus minus j 0.638. So the second answer is invalid. And after that, we found out the angle of departure from the pole -1 plus j1, and this is the answer that we got in negative. So in terms of positive, we will be getting 315. Okay, so this is the root locus that we were able to draw. Okay, uh, next, from this root locus, the question asked us to determine the location of dominant poles for damping ratio uh, 0.42. So from the damping ratio, we can find out the angle, and the angle that we got is 0.6517 degree. So when we drew the line it intersect at the uh, point stated here, which is the location of dominant poles, which is negative 0.45 plus minus j 0.95, and at that position we got the gain equals to 0.45. Next, the question asks us to identify the parameters which elaborate the performance of the system that refers to the transient response. So in transient response, we will be finding out the TP and TS, but to find out the TP and TS, we need to know the WD and W, the first one over here, the WN and also WD. So for the Wn, we can take straight away take from the equation that we get just now, or the from the location of dominant poles, which is 0.45, and the WD is 0.95. So the TP that we got is 3.31, and the TS that we got is 8.9. And also the overshoot that we got is 23.37. So next we uh, found out the uh, parameters that are related to the force response, which is the steady state error. So to find out the steady state error, we have to find out the Kp first, and we have to substitute all the S with 0 and the K with the gain that we got just now. So we got 0.5625, and to find out the ESS, we have to use this formula 1 over 1 plus Kp, and we got 0.64. So to prove our answer with MATLAB, this is the coding that we used, and also this is the uh, results that we got. So for, let's say, the EASS, just now we got 0.64. So over here it is stated the final value is 0.37. So when we take 0.37 and minus with 1, we'll be getting 0.64. And the overshoot that we got is 18.4. The settling time that we got is 8.1. The rise time is 1.63, and the peak time is 3.98. All this is for damping ratio 0.42. So that's all for my part, sir. Um, thank you.
Okay, hello sir, I'm Pavinten here. Moving to the next slide, we can conclude that the system performance to the root locus that uh, we get before through MATLAB and also to the drawing thing, we can see that the root locus is unstable. So yeah, it's unstable because it has a high overshoot value and also um, time peak time and also settling time. The steady state error is also high. So to improve the system's performance, we have to add a PID controller. A PID controller can be executed by adding two zeros and an integrator in the system, where we will add a zero near to the origin to decrease the steady state error while adding another zero around the real axis to improve the transient response. Uh, the first step in the theoretical way in adding a PID controller is by adding a PD controller first before adding a PI controller lah. The overshoot we want is 5%, so we want less than 5% overshoot in our system's performance. From that, we can from the overshoot we have fixed, we can find damping ratio. Through the damping ratio, we can plot on the root locus and get the dominant pole. And through the dominant pole, we can find the damping frequency and also the natural frequency. Then we can get the settling time, peak time. Then we want to improve the settling time value by 3 over 9 factor of the old value. The old value is the one we got from the root locus, where the initial one using without using any controllers. So we have to multiply the old setting time with the new one. Then we can find a new dominant pole through that. So we will multiply time settling, the old time settling, and you will get new one. Then through the new one we can find uh, the new dominant pole. After that we can find, we have to find the angle of zero that we have added. So basically PD controller is adding a zero in the real axis, which will decrease the transient response. It will improve the transient response with decreasing overshoot and also time settling while peak time. So we can get the PD transfer function as below. So we got S plus 0.74. So these are the steps that we overgone. Then we have to use the same method to find PI by adding PI controller and getting PI transfer function. So we get PI transfer function as K in bracket S plus 0.01. Okay. Then after that we can multiply all the three transfer functions together. The three transfer functions are the basic transfer function of the system GS times with multiplying with compensated with PD controller transfer function and also PI controller transfer function. Okay, so we can prove this method in MATLAB. So after proving in MATLAB, we got the same answers for all the parameters like overshoot, time settling, rise time, peak time. We got everything near. It's not exactly the same answer as we have calculated, but there's a mere changes and decrease and increase like plus minus in the values. Like the overshoot we got from the calculation is 5, and here we got 5.01. So there are a bit of differences. So next part is the implementing part, where we will be applying our transfer function in a operational amplifier. This amplifier consists of several parts, but the main part is the impedance Z1 and Z2. So for our case, it's PID controller. So we will be using two capacitors and two resistors. And one value of a capacitor we will be like assuming after undergoing some linear equations. So these are the linear equations that we have gone through. So this is the basic PID transfer function. So after expanding the transfer function, you'll get in this form, which this one refers for uh, K KD value. This one is KP value. This one is KI value. Then this is the basic transfer function. This is the basic equation in this operational amplifier form. So we have to change this. We have to adapt this transfer function that we got into this. So these are the method that we use by assuming C2 as 10 microfarad. So we got the values as below. So we will get the values for C2, R1 and R2. So we will successfully merge all those values and form a Z1 and Z2 operational amplifier values. So thank you. So,
Morning, sir. My name is Misha Vaniki Thomas. Today I would like to explain about my part E. So first I would like to share my MATLAB. So this is my MATLAB. So first we need to set the gain. Need to set the gain on. So we already set the gain on. So then need to click the bot editor So click the plot. This is our board plot. So if you see here, the gain margin and phase margin, the system has a gain margin 7.6 dB and the phase margin is 94.1 degree, which indicate that the system is stable and meet the stability criteria. So the damping ratio we get is 0.405. So we need to adjust the damping ratio. Our damping ratio is 0.453. So now we see the 405. So now we see the hot plot. So the gain margin is 13.5 dB and the phase margin is infinity. So high phase margin ensure that the system has a slow response and does not oscillate, while a high gain margin ensures that the system can handle disturbance without becoming unstable. The damping ratio of 0.405 show that the system has a good damping characteristic and the value of gain K that cause this damping ratio is 0.50152. In conclusion, the system has good stability characteristics with a high gain and phase margin and a moderate damping ratio. This suggests that the system has good performance and is suitable for the internet application. So that's all from me. So I pass my presentation to my co-presenter.
Okay, now I'm going to suggest an appropriate controller that can be used to improve this system performance, and I'm going to explain about the perform the design using a board plot. So to improve our system, we use a lag compensator. Using a lag compensator, we can improve our steady state error and static error constant. So as we can see here, our uncompensated board plot for magnitude plot and base plot, and also uncompensated magnitude plot base plot. Now to improve the static error constant, we use the lag compensator. First we find the phase margin for our required using this formula for the temperature of 0.405. Then we can find a new gain value. Using this gain value and the phase margin value, we can find the required gain margin value. And to improve the steady state error, we use this formula, which is to find kV volt, which is 1.4, and then for kV new value we use factor of 10. So using this we obtain our kV new value is 11.2. So now our new desired phase margin is 43.58 and plus 10 degree. So our new phase margin value is 53.58. From the plot, the value of the phase margin at the frequency of 1 radian per second. At this frequency, the magnitude plot is 3 dB. Thus, the lag compensator must provide minus 3 dB attenuation. So for the high frequency, the assembler at 3 dB at frequency of 0.12 radian per second. So the compensator must have a gain unity to retain the value of kV from the graph. The lower frequency is found at 0.0 radian per second. Here the transfer function is for the GC, which is compensated transfer function, is 0.078, then S plus 0.12 over S plus 0.08. So here our complete compensated transfer function, which is we can see here. So using this transfer function, which is compensated transfer function, we plot the board plot diagram in using MATLAB. And for the design using board plot using in MATLAB, we design the lag comparator in this board plot. As you can see, the result here at the output response, our steady state error is reduced. So it is close to 0.9. And then also our transfer performance also improved. You can see this is our compensated board plot diagram. And then for the implement of the designer controller, we use this operation amplifier method. So for the lag compensator, this is the formula for the lag compensator for the operating amplifier. So we assume our C1 value is 1 microfarad. Using this value, we can obtain R1, C2 and R2 value. So by using this value, we can substitute here and then we can implement our controller in this operational amplifier method.